Hello, from the last video, we had some numbers that were multiplying. We call them coefficients because we're going to multiply them out front of our probabilities. And we got 1, 4, 6, 4, 1. Now, how did we get those values? Now, some people may have learned about this before, but it's the number of ways of arranging k-successes in n observations. This is called a binomial coefficient. AP a lot of times writes it like this, and Algebra 2 we spent a lot of time writing it like this. But this is the formula. You take n factorial, so like 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, all divided by n minus k factorial times k factorial, and also in the denominator. And it can also be found with Pascal's triangle. Now, I'll show you a quick Pascal's triangle, and then I'll show you how to do it on the calculator. So Pascal's triangle is a little triangle that starts with ones on the outside, and then you add the two top numbers to get the one in the middle. So 1, 2, 1. This is always ones on the outsides, but if you add these, you get 3 and 3. If you add these, you get 4, 6, 4, 1, and so on and so on. And these are the numbers that are the coefficients. So our last one, since we were doing 4 different problems, this is the row with the 4 in it, so it's 1, 4, 6, 4, 1. Now, if you want to find those with your calculator instead of doing Pascal's triangle, what you do is you hit Math, go over to Probability, and it's NCR. And actually, we need to do something before that. We have to hit the first one. So if we did 4 NCR 2, that's 4 choose 2, and that's 6, which is the number in the middle. Or if we did that again, we can just hit second enter and we get the whole thing up. And we do 1, we'll get the 4 that's here. So this is a way that we get what we multiply out in front. Now, one important thing is to know that 0 factorial is defined as 1. So whenever there's a 0 factorial, we just use a 1. Now, what we did in the previous lesson was what we call a binomial setting. There's some things that have to be true if we're going to do a binomial setting. Each observation either has to be a success or a failure. Either you get the question right or you get it wrong. You make the basket or you don't. And sometimes your success is looking for something very that's not fortunate. Like if you're trying to figure out how many times you would lose your keys in a month, a success might be losing your keys, even though people don't usually look favorably upon that. There's also another thing that's really important with binomial settings. There's a fixed number of trials. In the previous problem, there was 4 questions that we were doing. And then we have to assume that each observation is independent, knowing one answer does not change the next. And the probability of success change is the same for each observation. And that these two kind of tie in together, because if they're independent, each time you find an answer, it doesn't change the next probability. Now, it's important to notice a binomial setting because there's some rules that help us simplify some really difficult probability problems. The notation is kind of like normal, but now we have a b, and we put the n, the number of observations, and comma, the probability. Forgot a g there. And we'll go through a couple like this. For example, if a couple has 5 children, the mother has type O blood and the father has type A blood, there's a 25% chance that the kid will end up with type O blood. Is this binomial setting? Well, let's assume that each kid is independent. There's a fixed number of trials. We'll assume that the probability is 25% for each kid. So, and our success here is they have type O blood. Our failure is anything else. So we're going to write it in the form, but it's a binomial with 5 trials, and the probability of success is 0.25. Let's try another one. If we deal 10 cards from a deck of 52 cards, and X is the number of red cards, is this a binomial situation? Now, you're dealing 10 cards, so it's a fixed number. You have success, red card, black card, so that fits. What this doesn't fit is independence. or the probability is staying constant. The probability is going to change by each card that comes up. So if you deal one card and it's a red, that's going to change the probability that the next card is going to be red. So we can't say that this is an independent situation. So we're going to say no. Now this one's a gray area one. An engineer inspects the barrel of 10,000 switches where 10% of them are bad. He chooses 10 switches to test to see if they're bad. Is this the binomial situation? This is just like the last one, but instead of having 52 options, now there's 10,000 switches. So when he takes one out, now the probability is going to go down, but it's not going to go down by much. So it's not independent technically, but we'll treat it as if it's independent because the probabilities really aren't affected that much. So is this probability? Is this binomial? Uh, kind of. Probability. It's binomial enough, and so we'll say it's binomial. They have 10 switches that they're dealing with, and the probability of success is 0.1. All right. Hopefully you can do your on your own.